Natural frequencies and resonance, exploring vibration behaviors in mechanical systems. Natural frequencies and resonance, agenda, introduction to resonance, plant resonances, critical speed concepts, why resonance matters, natural frequencies overview, describing natural frequency, mass-stiffness relationship, mode shapes overview. The key engineering theme of natural frequencies and resonance, presenting the foundational context for understanding how mechanical systems behave when subjected to dynamic forces. The concept of natural frequency describes the inherent oscillation rate of a system when disturbed but not continuously driven, and forms the cornerstone for predicting resonance conditions. Resonance occurs when an external force or vibration matches this natural frequency, often amplifying system response to hazardous or damaging levels. This presentation builds upon these central ideas to explore how engineers identify, test, and correct resonance-related problems within industrial or mechanical environments. By establishing this conceptual starting point, engineers and maintenance professionals gain the framework necessary to diagnose vibration issues, analyze mechanical behaviors, and implement preventive or corrective strategies. Additionally, this slide sets audience expectations for the depth and scope of material covered throughout the presentation, preparing them for a structured technical exploration. The agenda outlines the complete flow of the presentation, ensuring participants understand the structure from initial definitions to advanced diagnostic and mitigation techniques. Key topics include an introduction to resonance and natural frequencies, exploration of plant resonances and critical speeds, detailed discussion on mass-stiffness relationships, analysis of mode shapes, and a review of resonance detection methods. It continues with field testing approaches, such as impact testing and bump tests, followed by engineering correction strategies like structural modifications, stiffness adjustments, mass tuning, and damping enhancement. A real-world case study is included to contextualize these principles in applied engineering practice. The agenda concludes with a summary of critical learning points and a non-copyrighted reference list. By presenting this roadmap, the audience is guided through a progressive learning journey, improving comprehension and retention of the technical material. Resonance is a phenomenon observed in mechanical systems where the amplitude of oscillation significantly increases when the frequency of an applied force aligns with the system's natural frequency. This introduces a potentially hazardous condition, as even small external forces may produce large vibratory responses if resonance is triggered. Engineers must understand the physical mechanisms behind resonance to prevent structural fatigue, equipment malfunction, or catastrophic mechanical failure. This section introduces resonance using relatable engineering examples, such as rotating machinery, structural components, and piping systems. Emphasis is placed on how energy transfer efficiency increases dramatically at resonance, driving high-amplitude oscillations. The content sets the stage for later sections that explore how to recognize, measure, and mitigate resonance in operational environments. Plant resonances occur within large industrial installations where equipment and interconnected structures share vibratory pathways. Even if individual components operate correctly, the combined system may produce unexpected resonant frequencies due to structural coupling. This includes floor resonance, baseplate interactions, pipeline support flexibility, and equipment-to-structure feedback loops. Understanding plant-level resonance is essential for engineers responsible for facility reliability, as these broader interactions may not be evident from isolated equipment analysis. This slide explores common causes and symptoms of plant resonance, emphasizing the importance of considering the entire mechanical ecosystem rather than evaluating machinery in isolation. Techniques such as modal analysis, structural evaluation, and operational deflection shape studies are introduced to illustrate how engineers detect and characterize plant-wide resonance behaviors. Critical speed refers to the rotational speed at which rotating equipment, such as shafts or rotors, naturally resonates. When machinery passes through or operates near its critical speed, vibration amplitudes rise sharply, posing safety, reliability, and operational challenges. This slide provides a conceptual overview of how critical speed arises, relating it to shaft stiffness, mass distribution, support flexibility, and bearing characteristics. The content explains that many machines must pass through critical speed during startup, necessitating careful engineering design to minimize dwell time in this dangerous region. Understanding critical speed allows engineers to appropriately select bearings, set machine operating ranges, conduct balancing activities, and predict failure risks. This foundational knowledge supports later discussions on vibration testing and corrective structural modifications. Resonance poses significant engineering risks, making it vital to understand and control. Operating near a resonant frequency increases vibration amplitudes, which accelerates component fatigue, causes misalignment, loosens fasteners, damages bearings, and may result in catastrophic failure of mechanical systems. This slide emphasizes that resonance is not merely an academic concept but a critical real-world reliability concern. It explains how resonance contributes to maintenance costs, unplanned downtime, and safety hazards in industrial environments. Furthermore, this content highlights the importance of predictive maintenance strategies, vibration monitoring programs, and modal analysis to reduce operational risks. Understanding why resonance matters motivates engineers to develop proactive diagnostic and mitigation strategies to maintain equipment longevity and plant stability. Natural frequencies are the inherent frequencies at which a system oscillates when displaced from equilibrium without ongoing external forcing. Every mechanical object, regardless of size or complexity, possesses one or more natural frequencies determined by its mass and stiffness distribution. This slide explores how these frequencies are mathematically and experimentally determined. It introduces the concept of multiple modes of vibration and explains why higher-order modes may become relevant in machinery diagnostics. Engineering examples are provided to illustrate how natural frequencies influence machine design, such as avoiding overlap between natural frequencies and typical operational excitation sources. The content lays groundwork for later slides discussing mass, stiffness interactions and mode shapes, preparing the audience for deeper analysis of vibratory response behaviors. This section provides clarity on how natural frequency is described, measured, and interpreted in engineering practice. Definitions are given for fundamental frequency, harmonic frequencies, and modal parameters. Methods for describing natural frequency include analytical formulas for simple systems, finite element models for complex assemblies, and experimental modal testing for real-world structures. The slide explains how natural frequency descriptions are essential when comparing theoretical predictions with measured vibration responses during field investigations. Practical considerations such as boundary conditions, support stiffness, and added mass effects are included to help engineers understand deviations between expected and observed natural frequencies. This detailed explanation assists in building a comprehensive foundation for the upcoming section on mass-stiffness interactions. The mass-stiffness relationship is fundamental in vibration analysis, as natural frequency is proportional to the square root of stiffness divided by mass. This slide explains this relationship in depth, using conceptual examples to illustrate how increasing stiffness raises natural frequency while increasing mass lowers it. This principle is critical for predicting resonance and designing mitigation strategies. Applications include tuning machinery away from excitation frequencies, adjusting system mass distribution during balancing operations, and reinforcing structural components to increase stiffness. The content also highlights how engineers model mass-stiffness dynamics when analyzing complex equipment or plant structures to avoid resonant conditions. Understanding this relationship supports proper engineering judgment for corrective action selection. Mode shapes describe the deformation pattern a system undergoes at a given natural frequency. Each mode has a unique shape representing how individual points move relative to each other during vibration. This slide explores why mode shapes are crucial for diagnosing vibration problems, as they help identify the exact location and nature of resonant motion. Engineers rely on mode shapes to determine optimal sensor placement, identify structural weaknesses, and develop mitigation strategies such as stiffening, mass relocation, or damping treatment. The content highlights that mode shapes may vary significantly across modes and are influenced by boundary conditions and geometry. This conceptual foundation prepares the audience for diagnostic techniques discussed in later sections.